in this presentation, I will talk about collective decision making and how framing the problem differently allows us to significantly improve the performance over previous methods. This work should be seen as a follow-up on our other work presented at this conference called Improving Collective Decision Making by Using Confidence and Value Estimates. So first, some background knowledge on the problem we are dealing with. So we are concerned with decision making. Concretely, we are given at each time step a context to the problem we are trying to solve and a set of alternative decisions we can make. So each decision gives us a different outcome or reward defined by an unknown function f, and the aim is to consistently pick the best option from the set of decisions. To give you a concrete example, in medical diagnostics, we are dealing with ill patients, and the goal is to select the most appropriate treatments for each patient. So, for example, the treatments with the highest possible success rate. So, such problems are referred to as contextual bandits. You observe context, which define the decision you can make. You make a decision based on those contexts to try and maximize the reward you collect, and you repeat this over t steps. Now, typically these problems are solved by learning to map context to expected outcomes, so essentially approximating the reward function f. However, when the problem cannot be meaningfully captured by a set of features, or the mapping is too time intensive to learn, these approaches become infeasible. So what we are interested in here is solving such problems by exploiting the knowledge of experts. So at each time step, experts observe the problem's context, which can be something abstract like a set of features or something more concrete like a textual description. And then based on the context, they provide advice, which is either a probability distribution over the possible decisions or a value estimate for each decision, which is an estimate of the expected outcome of a decision. So, for example, saying something like, I expect decision A to have a 90% success rate. The goal of the collective decision-making system is to use this advice to make the best possible decisions. Right, so one way of using this advice of the different experts is to average it and then make a decision based on the average probability or the average value. However, if experts are unequal in their expertise, it makes sense to not weigh the advice uniformly. So in that case, the standard approach is either to learn weights based on the expected performance of the experts. So because we make t decisions, we have the opportunity to learn which experts' advice reflect reality and increase the weights of these experts in the decision making. So concretely, we can compute a weighted average of their advice and then make a decision. So previous work has considered either learning these weights, as in XP for P, or in the other work represented at this conference, we propose to exploit confidence estimates as weights. So experts tell us how accurate they expect their advice to be, and in function of this, we more heavily weigh the advice of experts with high confidence. So we also proposed XP4P plus con, which is a hybrid method which uses the confidence as priors on the weights it trains. As such, it is able to diverge away from the inaccurate confidence estimates if necessary. Now, fundamentally, all of these methods combine advice in the same manner by trying to find the appropriate weights to use to compute a weighted average of advice on which they then act. So in our work, we considered an alternative approach. So rather than strictly limiting ourselves to weighted averages, we wondered if stating the problem as a more general regression problem would allow us to obtain more accurate estimates of the outcomes. So what we identified is that the problem of deciding with expert advice is a contextual bandit in itself. Indeed, in addition to the base problem we are trying to solve, we are given a set of context, which is the expert's advice, and based on that context, we must select one of the alternatives. So, in addition to the mapping from context to outcomes, which is the base problem, we also have a possible mapping from advice to outcome. And so in this work, it is that mapping that we try to approximate. We essentially define a meta-contextual bandit, which is a secondary bandit whose meta-context are the expert's advice. So we essentially assume that the outcome for a given option described by its context vector can be approximated by some other function v, which takes as input the advice provided by the experts. And of course, this v could be the weighted average, but we do not need to restrict ourselves to that. So, because this is a contextual bandit also, we can solve it by using existing contextual bandit algorithms to learn the mapping v by balancing exploration and exploitation to ensure the best outcomes. So several such algorithms exist. We report here the results using Lenaerts, which assumes a linear mapping from context to outcomes. So in this case, we assume there is a linear relation between expert advice and the outcome. Now, on to the experimental evaluation. So as for our other work presented at this conference, we use an artificial experimental setting, which allows us to control the number of experts, the number of arms, and how confidence is generated. So concretely, we train n artificial experts on an artificial bandit. We sample a set of possible decisions at each time step and ask experts for advice. And then based on that advice, we make a decision and observe a reward, which is the outcome of the decision we made. So for example, 1 if the decision was successful and 0 otherwise. Now, we measure performance in terms of regret. So we look at how good the best expert would have performed over t steps and subtract from that how the algorithm performed. So a negative regret means we outperformed the best expert. So let us first look at our baseline performance without confidence estimates. So we looked at either having lots of experts and few arms, which is on top, or having a lot of arms but only a few experts on the bottom. Algorithms in blue use probability advice. Algorithms in orange use value advice. So we have XP4P, which learns to weigh experts, and the weighted majority votes, which uses confidence to weigh the experts if it is available, and otherwise just computes an average of the advice. So both of these were previous methods. And in addition to those two methods, we consider our proposed Meta-CMAB, which treats the problem of collective decision-making as a meta-contextual bandit. And in addition to this, we also consider Meta-CMAB, which treats it as a meta-bandit. So what this implies concretely is to consider each expert as a possible option. And choosing that option implies exclusively following the advice of that expert. So we are essentially learning to identify the best expert, but there is no proper collective intelligence, as we only take a single expert into account for the Meta-CMAB approach. Okay, so the dotted line marks the performance of the best expert. So anything below 0 performs better than the best expert. So the lower the performance, the better. Okay, so the first thing we can observe is that Meta-CMAB significantly improves over the other algorithms, especially when value advice is provided. So the reason Meta-CMAB benefits more from value advice is that such advice is absolute, in the sense that the value advice for one possible decision does not depend on value advice of other decisions, whereas in probability advice, the probability of each arm is dependent on the probability of the other arms. Now, concerning Meta-CMAB, when there are few experts, it is easier for Meta-CMAB to identify the best expert, which explains the difference in performance compared to when we have several experts. So let's look at the performance now when we add confidence. So when we include confidence, the performance of XP4P and the weighted majority votes improve, as we showed and explained in our other work. However, the performance of the other algorithms improves less. So in the case of Meta-CMAB, this is because there is no correlation between the confidence and the expected outcome of a decision. So including the confidence has no effect on the prediction. For Meta-CMAB, we include confidence estimates as priors on the accuracy estimates maintained by Meta-CMAB, but found there was only a slight improvement in performance. Perhaps because the stochastic nature of Meta-CMAB allows it to diverge from the initial weights. And finally, while confidence estimates can improve performance, one should be careful as accurate confidence estimates are not always available. So humans, for example, have been shown to be biased in their self-evaluation, which implies that human experts might over or underestimate their confidence. So we looked at how noise in the confidence estimates affects performance. Our noise model samples for an expert with true confidence C and T a noisy confidence from a beta distribution parameterized by C and T and a noise level eta. So the plot on the right illustrates the confidence distributions for a true confidence of 0.8. So as we increase the noise level, the distribution approaches a uniform distribution. So what this means is that at high noise levels, the confidence is unrelated to the actual performance. So let's look at the consequences of such noisy confidence. Now, again, we evaluate performance in terms of regret. This time the x-axis plots the confidence noise level. So the further right we go, the higher the noise in the confidence. So what we confirmed is that just as true confidence had no large effect on the performance of Meta-CMAB, noisy confidence also fails to affect the performance of Meta-CMAB. So as a result, Meta-CMAB, especially with value advice, outperforms other algorithms regardless of noise levels. Similarly, Meta-CMAB is not significantly affected by the noisy confidence. So while the difference isn't as pronounced in the absence of noise, the stable performance of Meta-CMAB justifies its use, especially when we expect noisy confidence. So note that both in the many and few expert scenarios, Meta-CMAB is either on par or outperforms the single best expert. Right, so to sum it all up, we proposed an alternative to previous approaches, which were based on appropriately weighting the advice in a weighted average. We call this approach Meta-CMAB, as it constructs a secondary or meta-contextual bandit through which it solved the collective decision-making problem. Now, our experiments show that this method is able to compete with weighted averages based on confidence estimates and significantly outperforms the previous state of the art when confidence estimates are noisy or absent. Okay, so that's it. So we have another talk at this conference. So if you haven't seen it already, I would invite you to watch it also. Thank you.